Right. The title of my talk today is orbital motion of a goal. It's a heterodimer driven by a circular polarized light. I'm sorry that it seems that my topic is slightly off for the mainstream of the conference. But anyway, what I have in mind is I try to discuss two nanoparticles about the size of 100 nanometers, illuminated by some kind of light. And I would like to discuss their motion, how it happens. Actually, we found that depends on the size, size difference of two nanoparticles that will act a rigid body and translate directly even under the circularly polarized light, or they will follow the same direction as the polarized light or different direction. All depends on the size difference of these two nanoparticles. This effect is due to so-called plasmonic effect that says that when the metal nanoparticle in the medium of a dielectric medium, then under the light, there was shown electromagnetic field around the nanoparticle. So there was some kind of optical force, optical torque, and make the nanoparticle moving or something like that. So in the theory, I will say a few words about what I did on those things, and followed by numerical results. This is so-called surface plasma, the plasmonic effect, and the metal and the dielectric interface. When light shine on this kind of interface, there was some electrical field around the interface. We have did under the light, if there is nanorods, nanorods rotate, or two nanoparticles, they will come together, or some other people they will cluster nanoparticles, or even cause nanorod to bend because of plasmonic effect and then sometimes thermal. And also other research work by some other people. Anyway, basically, we are talking about electromagnetic waves. So I've started with the Maxwell's equation. After some manipulation, electric field and the magnetic field will satisfy these two vector Helmholtz equation. And then I will try to analyze the scattering field. So I use the method developed by Hafen in 1983 called multiple methods. With that, the scattering electric field will express as a bunch of linear combination of vector spherical harmonics with unknown coefficient. The work in this method is try to use a collocation point on the boundary and use some kind of numerical method to find all those coefficients. Once we find a coefficient, we then find the scattering field. And then I have primary as an incident field, and then we can compute time average Maxwell's stress tensor with total electric field and total magnetic field. With this time average of Maxwell's stress tensor at hand, we can then compute the surface traction on the nanoparticle and then optical force and optical torque, etc. All the numerical work, all the simulation is that we start with the multiple method to compute electrical field and magnetic field, and then we will find the Maxwell's stress tensor, and then we go with this equation to find optical force and optical torque acting on the particle, and to study what the dynamic motion of those particles. And then since the optical force and the optical torque change the particle position, so we have to update the location to find a new electrical field and then mechanical field again. We go step by step and to find the final position. This view graph is a view graph talking about what we did in analysis of dynamical motion of the diamond. Okay, anyway, I just skip it, too busy to say nobody were interested in those mathematics. So I just skip this one. Basically, what I have in mind, I'm trying to talk about means that the size of two particles are different. But in order to understand that, I will start with the homodiamond. So we're talking about two particles have the same size and under linearly polarized light. We have to understand this first. So I will consider the so-called gold diamond, two particles, we call it diamonds. Gold diamond in the waters, the radius of these two nanoparticles is about 100 nanometers, and I will illuminate it by a plane wave of wavelength 800 nanometers. This is what we found of their relative velocity along this line, along the line of the particles. We found that there are some place this velocity goes to zero. So I consider this point, and this point, and this point. And the point one, the velocity is zero at point one, also at point two. But there's another point here. The big difference is that this guy has a negative slope, this guy has a positive slope. Negative slope means that if I move forward to make that apart away, the velocity will getting less, so they will move less and less, and then coming back with a negative velocity. So this is really a stable point. But this one is not. When the particle moving apart, the velocity is positive, so that means that they will go further away. And point 1 and point 2 will be a stable point, and then this red line is actually the velocity of the mass center. It's there everywhere. So it means this particle, when this particle, two particles moving, the center of mass is fixed there. So I have some comment here. Yeah, something like that. This is the initial position, and then we found that they'll go there. And stay there. Time is wrongly is stable there. But at this point 3, oops. Okay. I have to go back. This guy. Okay. All right. So I will go to Heterodimer. That means the radius of two particles are different. The first one 150, the other one is 100. And again, on the linear depolarized light, I will try to start the relative motion of these two particles. And then this point and this point will be stable point. But at this time, we find that the velocity of center of mass is not zero during the motion until they are stable. So the whole system will move in. And again, the finally the distance of the two particles will be around the multiples of effective wavelength. So yeah, this is the two particles at the initial position. They will run in here, and then go like that. So the center of mass is moving from there to here, and then finally it will stop there. Okay. That's a for Heterodimer by linearly polarized way. So let's come to circular polarized light, but I will start with homodimer first. So that means we have the same size of nanoparticles. This time is right-handed circular polarized light. We can see that for 100 nanometers of field, these two particles will rotate the same direction as circular polarized light. On the other hand, when we have bigger nanoparticles, the dimer will run opposite direction to the circular polarized light. Okay, and we found that actually these two regions is the region of opposite direction to the polarized light is run from the size of the nanoparticle is from about 120 to up to 160. If the size of that is this big, then they will run opposite direction for size below like 120 or bigger than 180. They will rotate the same direction with the polarized light. Now let's come to the real regions of heterodimers, two different sizes of nanoparticles and the circular polarized light. One particle is 150 and the other is 100. So the situation would be the combination of two things. This one we have seen that different size of particle and the linear polarized light, the center of mass will move and that finally perpendicular to the linear polarized light. And under the circular polarized, we also see that if they are homodimer, means the two sides of particle are the same, they will rotate follow the direction of circular light if the size is small. So basically, circular polarized light, the plane wave, possess only spin orbital angular momentum, and they only induce particle spin. But when we have the two different sizes of nanoparticle, the unbalance of optical force will drive the center of mass moving. So the combination of these two effects will be like this kind of thing. They will rotate different direction or in let me see. Okay, let me see the first. If I fix the one particle is 100 nanometer, the second one is also 100 nanometer, 160 nanometer, and 120 nanometers. For this guy, there will be some direction. Then omega c is center of mass, the rotation speed of center of mass. And for this case, around here, the rotation speed is about 0. It's infinite, so it is in fact Gaussian line. And for the case here, will be negative rotation. When this one, the omega c is close to 0 somewhere here. So, okay. This is my cartoon over my animation. I don't know. So I put, yeah, can I?
Yeah.
No. Anyway. They were starting from here and like that, or starting from here and unity translation like that, or starting from here, the counterclockwise is opposite direction to my circular light. I put all the information in this map. This time the first particle is 150, and this size this part of the map is for the location speed of the center of mass, and this part of figure is for the radius of the motion. So we see that the first one is 150, and then if the second one is about 100, and here is this guy. It's counterclockwise motion, and the radius is about here. And for this one, the omega, the rotation speed of the center of mass is about 0, so there is no translation. And for this one, the radius of the rotation speed is positive, is negative. Here, this color is negative, so they will go this way. Okay. So this will go clockwise. This one is go only translation. Go here clockwise. So they all have the difference of this size of these two nanoparticles. Okay. This is my conclusion. The two nanoparticles go translation or direction of the light, different direction of the light, will depend on the size of that. So I'll stop here.
Okay, thank you. Any questions?
I think no.